Hello, everybody. Hope you're doing well. Glad to see you all again. Today we are going to look at how to implement variables and, well, in general, how variables would work in a language. And as a reminder, I do this like every time. If you have any questions, put them in the chat in Zoom, and I will answer them. Okay, so I hope today it will be a bit shorter than last time when it took like an hour and a half or more. But anyway, let's begin. So far, up to this moment, what we had in our language, our entire language was a single expression. So the program consisted of an expression which was a binary expression of some kind. Well, as it's written here, it was an additive expression, so like a plus b. But now we are moving past that. So any language, basically, it has its program is defined as a list of declarations. And we will do the same. So our program will be a declaration list. Of course, there are languages like say Python, which can have executable code at the top level, kind of outside any function. But as a general rule, we will follow it. Like we will have a list of declarations as our program. And this declaration list will be defined as a single declaration or a declaration list followed by another declaration. And this grammar is what you already saw in binary expressions and whatnot. So it's like a left recursive definition, which we will be able to deal with in our parser with simply a loop, which will kind of take this declaration thing and accumulate them as pieces of a list. Since we are dealing with variables, our declaration for now will be defined as a variable declaration. That makes sense. And every declaration, every variable will be followed by a semicolon here. We don't have to do that, but I thought it would be kind of like C++-esque or C-like to do. And why don't we have to kind of separate variable declarations with some specific thing? Well, because there's no ambiguity here. What I mean is a variable declaration will be defined as a keyword var followed by a name, an equal sign, and some expression. So our variables will be of automatic type, which is like auto in C++, which we infer the type from the initializer. And for that reason, we have to have an initializer for every variable, like no exceptions, no uninitialized variables in our language. Okay, and if, let's say, if we change a lot of variable declarations one after another, we don't really have to delimit them, separate them by any special character, but this semicolon that is there just, I don't know, it just looks neat. Okay, and yeah, no ambiguity because every other declaration starts with a keyword which is uniquely in that context and nowhere else. All right, so our variable names will be just identifiers. We looked at identifiers, I believe, in when we looked at the lexer. So I won't stop in detail here. So identifier is just basically a string of characters which starts with a letter or a underscore sign. And a variable name will be one of our primary expressions with literals, with parentheses. It's just a literal expression. If we define a variable called a, and then we see a, it's a primary expression in our grammar. And of course, ID expression is an identifier. Okay, so that's grammar, but since we are dealing with custom names now, we will have to introduce a degree of semantics into our language. Before that, parser handled everything beautifully. Now we cannot rely on the parser alone because we will have to do name resolution. And that's really simple. So let's say we have a variable defined like this. And then we define another variable like that. And the second variable uses the first variable as part of its initializing. So in order to tell that this x here is the same as this x there, we will have to, well, simply associate a specific name with with a declarator for that variable. So we will have a table similar to this. So name x will lead us to a variable declarator for x, and y for y, and so on and so forth. And so when we see some kind of name in our program anywhere addressed, we will go there and look up that name. And if we find a declarator, it means that we have a valid identifier in our program. If we don't, well, that's an error because we do not know what it is. Okay, so let's go and jump into our little project which we have set up here. And okay, so we don't need PowerPoint anymore. So this is what we have. This is what was in the presentation, a small program in our language. And let me just check if we, we'll just call this test parser function. I will start it for you and show you what we are going to get as the AST. Okay, so I will go step by step in the parser in a moment, but right now what matters here is if you look at the AST for our program right now, we have a variable called x, which is initialized by this literal expression 42. And this here is actually an address of the variable declarator in memory. Those addresses are unique, guaranteed unique every time you create an object, so we can use them as unique identifiers. And here in this AST printer, I'm printing this address of the declarator in order to identify it later when we see it referenced, so we don't get confused which variable is where, because later on, when we go to functions, we will have nested scopes, and variables with the same name will be able to be defined in nested scopes, like it works in other languages. So for variable y here, what we have is, well, its unique identifier and a binary as its initializer. And here's our x, and here's its address in memory. So this and this. So now we know that this name x leads here. Okay, so let's go into our parser and see how this parsing is done. And we will go to this program thing, because this is where we are going to start. Okay, so, and immediately what you see here is this instruction for SEMA to enter new scope. And I'll explain what SEMA is and what this all means. So SEMA is our semantic analyzer. It does basically, well, it deals with any type of kind of semantics which we have in our language. And it hosts the symbol table where we keep all our name to type associations for variables and functions. It also manages scopes. Right now, we will only have the global scope for variables. Later, when we go to functions, we will have scopes of function bodies, scopes of like nested scopes into function bodies for conditional operators, statements for if, for loops, for, I believe we can just create like a small block of code inside a function which will have its own scope. But that's for functions. Right now, variables. So let's go and look at what this SEMA thing does. Yeah, and the other thing SEMA does, it deals with data types, because our language has a static typing system, and SEMA helps us with that. Okay. If we go into this enter new scope, what we have here is if our semantic analyzer is fresh, kind of, which we have here, it doesn't have the global scope yet. We will just create one. Well, not create a reference one, because global scope is static in our program. And this is needed because we might want to parse, like we might want to run the parser consequently several times. And every time we run the parser and add something into our global scope, we should have just one global scope, the same, and not create anything new. Okay, so right now, yeah, we are entering global scope, and right now we have us a playground where we can kind of put things we declare. And now what we have here is this a bit of kind of functional programming. The parser has a function called list, which takes as input another function. In this case, we have a lambda, which implements the logic. So let me put this way. So when we will have different types of lists in our language. So we have declaration list, we will have statement lists, we will have parameter lists, we will have function argument lists when we call functions, and so on and so forth. Every kind of list in our language is built in the same way. So we iterate while some conditions are met. We count elements which we processed, and we then ask the builder of the AST to create us a list of this count of elements from its internal state, from its stack it has inside. And what differs, the only thing that differs between all those lists is how we handle this internal part. The logic of we apply to every list element. So this here is just a call to function, which is going to process all the boilerplate of iterating for us. And we will just provide it some logic which should be implemented at every step. So let's step in. Can I step in, please? Yes, I can step in. This list handler thing is actually, it's a concept which defines a function that has no parameters and it returns a bool. So any function which has no parameters and returns a bool is good to go here. So can push it into this list function here. And we also have a token which we are going to stop on if we encounter it. So for our declaration lists, this breakon token is set to end of file because we will be parsing the declaration list to the end. Like nothing else can happen there. This value will be different for different kinds of lists. So, for example, for a statement list, the terminal token kind of is a closing curly brace, I believe. So that's that. We'll just use it to tell it to stop and don't go any further if we meet it. Okay, so. Okay, so what this function does? Well, while we have anything, while our input continues, take a look at the next token. If it's our break token, we'll just bail out. And then we call our handler thing, okay? So right here, we will go inside the handler. And this if here, what it's going to do, it's going to consume empty declarations because we can write something like a long string of semicolons and then a declaration of a variable. So this thing will do just removal of semicolons we might have between declarations because we are not limited in the number of them. We can just type. Okay, so it's not a semicolon because obviously we have this var x. So we go and continue. For declaration lists, we of course call like we want to collect all declarations. So we'll go into this declaration thing here. Okay, and what we do here is we pick the next token, and in our case, it will be keyword var. If it's not, it might be a function declaration, which we will do next time. And if neither var nor a keyword for function are encountered at this level, at the global scope, it's an error. So anything we write here is an error. And that's why we had that, little if in our list lambda, because technically a semicolon would have been an error here. We just remove them to not have problems. Okay, so as you can see, our next token will be var, and we will go and look at what the variable declaration thing looks like. Okay, so the first thing we do, and you will notice this a lot, is we check the token, we go somewhere else, and we immediately remove this token. We need to go past the var keyword. That's why we instruct the lexer to drop the token it's currently at. So right now we are here at X. And now all bets are off, kind of. So we are in a variable declaration. If anything goes wrong from this point, we will report an error and handle it the best we can here. So we are not kind of doing any checks anymore. So we are here, we expect a variable, so we either get a variable or we get an error. Okay, so we consume the variable name here, it's X. And what we are going to do next is check if this name, well, first, if it's a name, otherwise it's an error. And we will also check that this name has not been defined in this scope previously, because if it has been defined in the same scope, it's a redefinition of a name. I will not go into scopes in detail right now, but let's say the name here, we know it's an identifier, so we will be past that. And here we will go into our SEMA again, and we will do something known as the scoped lookup. Again, next time when we look at functions, we will look at this scope and unscoped lookup. Right now, basically what it does is we take the current scope, go to our symbol table, and try to find a name for our variable there. And if the name of our variable exists in the symbol table, we check that it's in our current scope we given it. And if it is, we return what we found, an AST declarator pointer. If it's not there, it means that we have not found it. So in this scope, this name does not exist. We also have an unscoped lookup, the same thing basically, but we will jump scopes up until we reach the very top. And if the name exists in any scopes along the way, that's okay, that's name found. Otherwise, it's not. Okay. So right now we have, let's go and just do that real quick. So up. Again, we reassign this global scope here, which we don't have to do. But let's go to the symbol table. And our symbol table is basically just a associative collection which has names as keys and declarators as the values. It's a little bit more complex than that, but for now we will think of it as an association of the name and a declarator. Okay, so we look in this map name to declarator if we can find the name at all. If we cannot, we have not found the name. And this code here it deals with nested scopes, basically because our symbol table is not as simple as we think of it right now, but that's for next time. We will just look in detail how it's implemented. Okay, so right now we have not found the name, which means we are good to go. Okay, so our name is good, our keyword was good. Now we have to have an equal sign before the initializer. So again, here we are good. If we are not good, we will do an error. And now we are making an initializer for our variable. It's going to be an expression. And an expression is going to be 42. I think this. So we are here. I think we don't have to do it in detail because we will have to step quite a bit into the recursion to do that. We'll just know that that's 42, right? And now we have two possibilities, right? So we might have everything fine, or we might have errors along the way. And if we have errors along the way, we have to report them in our AST. Like when we encounter an error, we just create a node for it in our AST and mark the entire chain all the way up to top as invalid. And we want to report kind of all errors we've encountered for the most part. So that's why we count them here. And if we had any errors, we will not create a variable declaration. We will just create a list of nodes which will report all errors in that list. But right now, we are good to go. So we'll go to the builder again. And we will tell it to make us a variable. And in our state in the builder, if we can look at it, in the state, we have an initializer. I don't know if you can see it good or not, but yeah. Our builder right now, inside of it, it has an internal state where it stores ST nodes it builds, and it uses this state to shuffle them around and kind of link them together. And right now, what we have there is just the initializer expression. So let's see if we have an init in the builder, of course. We have it, so it's okay. And here is the other thing Sema does. For anything which might have a type, Sema is able to extract that type. Why do we need Sema to do that? Well, because we don't know what's here, what's in this variable. We don't know it in advance. We cannot guarantee that it has like anything we might want to expect of it. It might be an error, it might be a list of things, it might be anything at all. Because we are operating the base class of AST nodes, and we have a visitor to deal with that. And to extract type from an AST node, guess what we are going to be using? If you saw the last, the previous webinar, previous talk, we looked at the AST visitor there. And this visitor, we used it to print the AST in the console, but we will be using it for all kinds of different purposes. In this case, what we use it for is to extract types from nodes. And so here it is, our type extractor. Basically, what we have, we have a type here. I will tell you about types. We have a type here which will be initialized on any kind of AST node which has a type, which is indicated by this base class called typed. Every AST node which has a type, so expressions, declarators, what else? I think nothing else. Yeah, any AST node class which might have a type in it is inherited from this typed base. And since our visitor works on overload selection for different types, which we give it when we cast, when we iterate through the tree and we cast every node to its real type from the base class, we basically invite the visitor to select the overload for preview and visit functions. This is how it works. So any kind of node which is inherited from this typed class will get into this function, and it will have its type extracted, because here we are no longer type erased as we normally are, because we are operating the base classes everywhere. Okay, so all it does, it just calls the base visitor operator. The base visitor operator does recursing, and then at some point we do or do not get here, and we return what we found. Well, in this case, our type is int, because 42 is int. Okay? So that's what this extract type thing does. So we get int, our right-hand side of our initializer is that. Okay, and now we will do some things, some more things here. So basically, we cannot assign from a variable, cannot be assigned from some kind of types. We will have type void, and we will have a special type for functions, and we cannot assign from those. So right now I'll just keep here, but this part here, it checks if we are assigning from something illegal. And of course, if we have an error, we'll just create a list which will contain our initializer along with the error, and it will go as the right part of the variable declarator. I think I'll show you, in a moment. Okay, and now we just extract the variable initializer from our internal state of the builder and create an AST node for the variable. And here is our AST node for the variable. So it's a variable declarator. It has an initializer, which is a literal expression. Yeah, so it has a name and it has a type. Which is, if we look at it, this is exactly what we are going to see. So we have an init here, and we are inherited from decal, which is inherited from type. So our variable declarator now has a type. And the next thing we are going to do with this variable is record it into our simple table, which is going to be happening here in SEMA, in record. It will take the current scope, which it keeps track of, because we tell it to enter and leave scopes as we go. And it will create an association with the name and the declarator in the given scope for us. So we have successfully created a variable now. And what happens when we address a variable? Let me find my ID expression here. Here it is. So when we address a variable, basically what happens is just a name lookup, or the identifier is undeclared. So if we look here, here's our X. And if we go parsing our code further, we will at some point arrive in the ID expression, which is happening in this spot. And we will want to know what this name X means. So we will just go into our SEMA again and look it up. And here we have found X, which has a reference to its declaration, to the place where it was defined. And again, if we don't know the name, it's an error. If we know the name, we'll just make an ID expression in our program. Okay, so let me show you, try to demonstrate something that can go wrong. Well, just delete that. Well, let's say we wrote something like that. So what we are going to have, see, this has errors marked here. So every time a node with an error is attached as a child to some other node in our AST, it will propagate this error flag. Basically, it has a bool inside. It will propagate it up, and it will mark the entire chain of AST nodes up to the very top as invalid. And we do that primarily because when we go and create our evaluator, we do not want to deal with incorrect code. So if code is incorrect somewhere in our program, We will create an AST for it, but we will never, ever try to, well, run it, evaluate it really. Because garbage in, garbage out is not the approach we want to take. Okay, so as you can see, what happened here is we ended up creating the variable because the variable itself was not drawn in any way. It had a normal name, it had a keyword and the equal sign. But what went wrong is our initializer here. And at this, in place of the left operand of our binary expression in this initializer, we have an error undeclared identifier because we were unable to find this name. Okay, so what else can go wrong? Let's go, if I write something like that. Oh, again, what happened here is we found the name X, we found this keyword. Those were good, but then we did not find the equal sign after the name. And so our var_decal function decided to go and generate an error. And if you look at this part, you see this list. This is our top level program, kind of. And this list is what was created instead of a variable declaration here. So it generated an error and it made a unary expression +1 because 42 was in place of the equal sign, and it just consumed it instead of the equal sign and said that okay. And now we also have a situation like that. So let me just demonstrate. We can try to have a function and assign from a function to a variable, but we cannot do that. So I know we didn't do functions today, but we'll do them later. So just believe me, functions are there. Okay. So what we'll have in our variable declaration is, as you can see, X was good, equal sign was good, but the right part, the initializer, was not good. So we say the initializer was a function reference ID expression, but we cannot assign from a function. So sorry, this variable is invalid. Or we can call this function here and have another error which says that we cannot assign from void because our function returns void. Yes, and here's our call expression, which we will not do today. I wanted to talk about types because we are starting to deal with them. In our language, types are really, really, really simple. We will have just basically this set of what we call types. Okay, so error, obviously, when we cannot determine, for whatever reason, when we cannot determine the type of something, it's going to be an error type. Void, it will be useful for functions which do not return values. So we will have functions which return void, and we will have functions which return not void. Okay, we will have also ints, floats, and booleans. Those are types of our values. And we have this generalized function type, kind of function type, which is not a real value type in our program, in our language. And or when we start mixing and matching types in our programs in our language, we will have to calculate their relationships to each other. So let's say we write an expression like that, 42 plus 4.2. So it's an int plus float. And look what we will have here. If we run it, what we will have here. So our binary expression will be float of the float type, and our integer expression here, this 42, will have to be cast to float from int. So both operands should be of the same type in order for us to perform an operation on them. And the resulting type, which we see here, is something which is present also in C++, and it's called common type. When we perform a binary operation over two operands of different types, the first thing we need to determine about that is what type they both can be cast to. Like the type which can represent both values. We need to figure that out. And that is a common type between two other types. And this is what SEMA also deals with. So let's take a look at this common type thing. So, yes, our types are literally just this, So we do not have class hierarchy or anything, because I wanted to demonstrate it as simple as possible. Okay, so how do we figure out a common type between different two other types? Well, we'll do some template magic here for C++ template magic. I'm not sure if you were to write the same kind of thing in other language, which is not C++, which doesn't have templates. You wouldn't be able to do that exact thing, a compile time template selection, but I guess every language has some mechanism which will allow you to deal with things like that. Okay, so for our base template, we will have just this structure just defines a value of our enum in it, which by default is, well, not by default, we specify it when we use this structure. So it will be used as a base structure for all our common type selection things. So it has a value inside it, and this value is of this type, of this enum. And in the general case, given two different types, we cannot know what the common type between them is. So in the general case, for two random types, they produce a common type of error. here. Now, for any given type, the common type of this type and itself, with a couple of exceptions, will be this. So a common type for int and int is int. But a common type between a function and a function is an error, because function is it's not a meaningful type in our system. It's just an indicator of that the name is associated with some function. We might change that if we want. If we wanted to create to make functions like a first-class citizen, as they say, if we wanted to be able to assign functions to variables, pass them around, and call them by pointer, reference, whatever, we could do something different here. But for now, functions gives us error. And now we just create templates, specialization for every combination of types which we might have, like every meaningful combination of types. So int and bool, or bool and int, gives us int. Int and float gives us float, because float is a more broad thing. It can accommodate int values, but int cannot accommodate float values. Bool float, of course, is float, and bool and bool will give us int and not bool. Why is that? Because we can, in our language, is legal to write true plus true, for example, and we will get 2. But in order to get a result from kind of arithmetic operations with Boolean values, we need to make them ints, basically, because true plus true is still true in Boolean terms. It doesn't make sense as in arithmetic means. Okay, so bool and bool, yes, it's going to be int. And also we will have those switch cases which will which will use templates in order to calculate common types between values from functions. So the way we use it, we have 2 type IDs, kind of. We call this function calc_ct, which is calc common type. It will do this switch case and dispatch using templates specializations into this function, which will call basically this function depending on what was the value of this and this parameter. And this function will just do the selection from this structure for us. So this is all done basically in compile time whenever we ask for a common type, except the initial runtime call to this function here. Okay, now the way we use that in the builder. So let's say we are going to a binary expression. Our case here, 42 plus 4.2. So we have parsed the left and right operand of that expression, and we want to create the expression itself. So what we do, we extract the right-hand side because it's a stack and the right operand is last in the stack. Then we extract the left operand from the builder state. And we go here to this semi-binary type function, which will give us something. And what it's going to give us is a structure called binary cast. The same for Yuri, but binary is more general. So what it will give us as a result of us asking it to create this binary type. So it will give us the resulting type of the expression itself. It will give us the original type of the left operand, and the type the left operand needs to be cast to. And the same for the right operand. We will also have the same thing for unaries, but a unary is kind of a simpler, really more simplistic case. Okay. So how it works? This. Oops, I lost it. It seems like I lost it. Let's do it again. Yeah, it's because Visual Studio is doing stupid things. Okay, so what we do is we extract type from both parts. Let's actually go there and let's go, in fact, here and do that. Don't need that anymore. So our left is 42, our right is a float. So we go inside this binary type thing. We extracted our types from left and right operands. So left is int, right is float. And here is the first catch we will come across for binary expressions. If we have a logical expression, something like, let's say, logical or, logical and, for this kind of expressions, if we write A and B, we know that the return type, no matter what, should be bool. And every operand should be cast to bool. So we do not do anything here. We just say that, okay, so expression type bool, left type was that, it will be this, and so on, so on. Otherwise, we are going to calculate the common type between a float and int. And in this case, it's going to be float. And this result type here, it's going to be conditionally set. So if we are dealing with like a normal arithmetic operation, like a plus b, whatever, the resulting type of the expression is going to be whatever the common type between the operands is. But for expressions like a equals b, or a doesn't equal b, or a less than or greater than, and so on and so forth, both operands will need to be cast to their common type if needed, but the result of this entire expression is going to be bool. So what's going on here is, if applicable, the resulting type of the expression is going to be set to bool, otherwise the common type which we have. In our case, the operation is addition, so it's not relational, it's arithmetic. So we will set the common type to float, like the result type to common type. Okay, so back to the builder here for the binary expression. if you can, as you can see here in this structure, expression type is going to be float. A right operand was float, will be float. We don't have to do anything about it. But left operand was int, but it should be float. So we will have to cast it to float. And we are going to take that cast and put it right into the AST, because for the evaluator later on, we do not want it to figure types out. We want it to walk the tree and simply do what's there. So the evaluator will just execute, it will do what it's told to do. So the AST will tell it, hey, take this value, cast it to this type. The evaluator will just do that. It won't be needing to do any type calculations of its own. Okay, so for this here, our binary, our left-hand side type was int, now it's float. If those two things differ from each other, then what we are going to do is create an implicit cast tree node in this specific place, in place of the left operand. And we will use this left operand as a child of this implicit cast node. So basically what we are doing here is we are creating another node which has a child as another AST node and a type to which this AST node is going to be cast. And of course, now that we have created a node as usual in our builder, it will going to be placed on the stack in the internal state of the builder. And we are going to extract it here. So it's an implicit cast node, and if we look at it, it just has an operand, and it's a typed thing, so it has a type from the base class. Our right-hand operand doesn't have any change in its type, so we won't do anything with it. And the when we create this implicit cast, of course, we overwrite our corresponding parts of the expression. Like if we cast the left one, the left will be overwritten in this variable, and same thing for the right one if needed. And now we create a binary expression AST node, which will have its left, its right, its operation, and its type, which is going to be float in our case. And we are going to be doing these things every time we need to have some interrelations between some expressions. So for example, if we call a function, we need to take its argument provided and convert them with implicit casts to types of the function's parameters. So if a function takes a float and we call it with an int, in the place where we call this function, the int will be wrapped in this implicit cast to float. As a result, we will have what I already showed you. We will have this implicit cast to float. And the way we are going to evaluate this thing, our evaluator, when we get to it, which is going to be in a couple of meetings with you, it's going to go here, go all the way down to this value. It will calculate, okay, 42, go back up. It will see, oh, cast 42 to float. It will cast the value to float. it will take this value, it will go back here to the binary, it will perform the operation we told it to perform, and yeah, it will be assigned to a variable. Okay, so for unaries, same thing, basically, but for unaries, we will have a special case for this exclamation mark, the unary Boolean negation operator. So let's see. Show you not before. So if we write something like that, our unary expression, since it's a logical, the same thing as for binaries. For logical expressions, bool is the result. So yeah, the resulting type of the entire expression is going to be bool, and we will have to cast this int to bool, basically. But if we do something like that, minus true, why not? We will cast this bool to int, and that's why I showed you before. A common type between bool and bool is int, also for those cases, because the unary operator result for an arithmetic operation is a common type of the operand with itself. So if we have minus int, it's going to be common type int and int. So the expression minus 2 is int. But if we have something like minus true, then the common type between bool and bool is int, so the expression itself is int. And we will get minus 1 here when we evaluate the code. All right. So I think in order to not stay here for another hour, as we tried last time, let's finish here with variables. And next time we are going to get into functions, and I will show you, I think for functions we will spend most time looking at this symbol table and how it works with scopes. I think maybe not, but we'll see. But yeah, for next time we are doing functions, and since we are doing function implementations also, their bodies, then we are going to look into statements our language has. So yeah, for now, that's all from me. And if you have any questions, again, write them in the chat. And what I have from Alder is, what notation is this? I have no idea what it is about. It's 5 minutes. I guess it's, yeah, the question was, I guess, about the grammar notation I use. Since Alder is not here, I will answer it anyway, even if Alder is not here, so everyone else knows. The notation for grammar that I use is the same thing used in C++ standard for C++ grammar. And I'm using it because it's very close to plain English, and it's very easy to read and understand, instead of using something like really math heavy. Okay. And Stefan, thank you for presentation. How can we generalize the common type system that you showed with template specializations to cases where there can be multiple conversions in one operation. Like in C++, where you can have a conversion from a user-defined type to a standard type followed by a standard conversion. You perform every conversion step independently in these cases. So it's a chain of calls. For the common type itself, it's going to be basically the end result of this. So you calculate common type between between two types, like we are doing here, basically. Minus the C++ is much more elaborate type system, where you cannot really do like template specialization thing we are doing here. It will be inevitably something more complex. For simple arithmetic types, yes, you can just have template specialization, just like I have here. But you will have to add some logic, which will, for example, go and look up for any conversion function in a class if you are converting between classes and so on. So no easy way. But anyway, yes, and common type in C++ is calculated really in a nightmarish, very complex fashion. There are many rules, so you cannot really do just template specialization for everything. But when you calculate the common type, what you do then is you perform according to the standard in C++ and in other languages, I would imagine. You perform steps of conversions. So you go little hops, like for example, I don't know. So you go from a variable name to, which is int, to a float, right? So you have to do L value to R value first on the variable. So you get an R value, you go and then perform an int to float conversion, and if needed, you might be adding a reference and so on. So yeah, that's the long answer. The short answer is, I guess, there's no way to use in such a complex system a simple template specialization. You have to do runtime calculations inevitably. Between ints, float, between built-in types, you can do literally like the same thing we did here, because built-in types are kind of easy-ish. They're not like really easy, but they are much easier than anything else in C++. I was doing this conversion sequences, by the way, from and to classes recently, and yeah, it was fun. Yes, and I hope, Stefan, it makes sense what I just said. Okay, so so next time, like I said, I was thinking of how you find the middle type in a two-step conversion. I know what you mean, but there's no middle type, really. There's no such thing as a middle type, because you do not do, like in like C++, you do not do step-by-step type conversions. Conversions are a broader thing in C++. So you do not go like from, let's say, from bool to int and then to whatever, I don't know, float, or from bool to int to long to whatever. the standard specifies that integer promotion, right? And so on. What you typically do is every type which is an integer and less than int is going to be cast to int. Int is a special case. And then you calculate the common type of int and whatever else you have. So, and those little conversions, like say from short to int, they will not be reflected in the conversion sequence. You will just have like integer promotion, and that's it. And the common type, when you calculate it, you kind of go and promote everything which you need, and then you calculate a promoted type and common type. So it's not like you have a chain of small casts. You have a promotion maybe, and then a conversion to the common type. So it's not, and yeah, and for a promotion, again, there is a set of rules which you have to implement when you do promotion. The standard, thankfully, is, well, in C++, at least, is very, very specific and quite elaborate. So if you just go and do it by the standard, step by step, you can do it. You don't have to invent anything, at least, thankfully, because they laid out the exact sequences we need to do for us. All right, so I guess that's it for today. And I'll see you next time. I'll wait just for a minute, and if oh yes, bye. So Thomas said bye, and I guess I'll say bye to you too. So